Alright, so in this video we're going to discuss the parallel axis theorem. Now on Blackboard you have linked a set of mole of inertia equations for different shapes. But what happens if I ask you a question about an object rotating about a point not provided in the list in Blackboard? Well, one technique to handle that is to apply the parallel axis theorem. That allows you to take an equation of mole of inertia you already have, so say for a solid cylinder, and if the axis is, say, instead of through the center like it is provided in the table along the edge, you can make a new formula and be able to solve the problem. Now this is called the parallel axis theorem. So whenever you move the axes from a known equation to the situation you want to apply it to, the original axis and the new axis have to be parallel to each other. So if it asks you to do something where you're moving the rotation point or rotational axis that perpendicular to the original axis, then this theorem does not apply and you can't do the problem. Alright, so what I have set up here is a coordinate system for us to work with. Now I'm focusing in on a couple of points. You have to imagine, say that this right here is the center of a solid sphere, and this is a particle within that solid sphere. So the whole thing probably wouldn't even fit on my paper. So you have to imagine that I'm focusing in on just a couple of key points where this is the center and this is some arbitrary particle within that solid object. Alright, so the first point I'm worried about, is I've already pointed out, is the center. And this is what we refer to as the center of mass. And so for a symmetric object, homogeneous symmetric object, the center of mass is going to be at the center. If it's not homogeneous and symmetric, then you're going to see that the center of mass is shifted not from in the center of the object, or what looks like the center of the object, but more towards the point where there's more mass, because essentially you're setting up a point where there's equal mass all around that point. But I'm going to stick to symmetric objects because those tend to be the types of objects you have the mole of inertia equations provided for you. So this is our center of mass, and this is where the original rotation point would be. So as I'm trying to use a solid cylinder as a visualization, this would be at the very center of that sphere, and you would have the rotation point going into the page through that point. Now say, instead of having the rotation point be through the center of the sphere, the rotation point is, say, halfway between the edge and the center. So we've moved it some parallel distance away that we're going to call d. And we're going to set up the coordinates for that new rotation point to be a and b. So a is your x, b is your y. Alright, now we're going to focus in on one arbitrary particle within that solid sphere. I'm just using a sphere as an example. And so I'm labeling it mi because you're going to iterate over all particles within this sphere. And so its coordinates are just going to be arbitrarily x and y. Once again, the i's are just indicating that you're iterating over all particles. So each particle is going to have its own coordinate that makes up this solid sphere. Alright, so since we're looking at one particle within the system, we're going to use the point mass equation initially. So mole of inertia is going to equal m r squared. So this is the equation for a point mass. Alright, so if we look at the moment of inertia about the original axis, our particle is going to have mi, so that's our mass of one particular particle, times the square root of xi squared plus yi squared. And then we're going to square that. Because remember, the distance from here to here is going to be the hypotenuse of a right triangle where this is your x coordinate and this is your y coordinate. So if we take the two sides of the triangle, we can use Pythagorean's theorem to find the distance between the center of mass and the particle up here. And I know the square root and the square cancel each other out, but I write it like this just so you can visualize that I'm plugging in something from Pythagorean's theorem into that r squared position. Alright, so now we're going to write down the mole of inertia about the new position, so when we've moved the rotation point. And I should point out here, eventually we're going to sum over all particles. We're going to start out with that concept here. But our values, our distances, are a little different because we need to go from here to here now rather than from here all the way up to here. So if from here to here is A, and from here to here is xi, from here to here is xi minus A. And if from here to here is y, and from here to here is b, then from here to here is yi minus b. So this is going to look a little messier. So xi minus a squared plus yi minus b squared. And then we're squaring that entire quantity. Alright, so now I'm going to do a little bit of algebra, where I'm going to acknowledge that the square root and the square cancel each other out, and I'm going to FOIL these terms in here. Alright, so let's see what we're doing down here. Alright, so don't forget we're eventually going to sum over all arbitrary particles. Alright, so let's talk about each of these terms. So let's focus in on our first one up here. Now let me do something real quick to this. I'm going to put this in parentheses, I'm going to take the square root of it, and then I'm going to square that term. I haven't changed anything mathematically, because a square and a square root cancel each other out. But it looks like this equation we had up here, which was a moment of inertia about the center of mass. So I'm going to replace this term down here with the moment of inertia of about the center of mass. So this is typically I think of this as the original equation, the one you get from the list in the textbook. Alright, so now we need to go off to the side and talk about how you calculate the center of mass. So I hinted for a homogeneous symmetric object, it's automatically at the center. But if you wanted to, there is a formula in order to calculate it. And you have to do each coordinate. Technically speaking, since I'm talking about a sphere, I should also be talking about the z direction. But it doesn't really change what we're doing with our formula. Now the thing is, we set up our coordinate system so that this and this are 0. So see how we picked our coordinate system? And I did that specifically because it's going to make our math a lot less complicated. It's not going to change what the answer would be. If I made the original coordinates 1, 1, everything would be shifted over by 1, which then in the end we'd have to subtract back off. So it's just easier to set it up so our center of mass is the 0, 0 position, especially since when you think about measuring like the radius of something, you think of 0 as being in the center and you move out towards the edge. So that's a pretty normal assumption. Now I want you to focus in on the top of this equation, the sum of the mass times the position of the particle, where you're summing over each individual particle mass times its position in the object. So you have this, and notice that matches this right here, and this one over here matches this right here. So I can say this is 0 and this is 0, because that multiplication and then addition of all the particles added together are the only way that can equal 0, because you can't have 0 mass. If not, what are we talking about? If you have 0 mass, there's no problem. So it's only the numerator that can lead to the position of the center of mass being 0. Alright, so that means this is 0, and anything times 0 is still 0. So we're going to add 0, or subtract 0, doesn't make a difference, subtract 0. Alright, now let's look at our last term here. Now once again I want to do my trick where I do the square root and then square it. So once again this looks like you have r squared and then you plugged in the hypotenuse of a triangle as r. And so if we look up here, this is A, this is B, And I can put B over here if I wanted to. Doesn't change anything, it's still the same length. But it's very more clearly a right triangle here where D is the hypotenuse. So I can say that the square root of the quantity a squared plus b squared is the same thing as D. So I'm going to put the mass, because the sum of all particles within the system is going to be, or the sum of the mass of all particles within the system is just going to be the total mass times D squared. Where very specifically, so let's rewrite this down here. Is the distance between the original rotation point and the new rotation point. And remember, those two rotation points or rotational axes have to be parallel to each other. Keep in mind, this here is the formula that you are applying when you're solving problems using the parallel axis theorem. All this up here was me attempting, at least, to explain where this formula came from.